In this session of video, I'm going to build prime number table. If we have prime numbers, we can do lots of cool things. For example, we can factorize integers, and also we can factorize polynomials, and also prime numbers are the basis of cryptography. In this session, I will explain the theory and I will implement the C code. In the next session, I will implement the same algorithm using multiple threading and I will optimize the algorithm. Okay. First, 2 is the smallest prime number, and 2 is 1 and only one even prime number, What it means, 2 is the smallest prime number and 1 and only one even prime number. It means that all even integers and greater than 2, all even integers and greater than 2 are not prime numbers. So in our algorithm, we will skip all even numbers greater than 2. Second, for all integers and greater than 2, if there exists S such that S times S equals N, then N is a perfect square and N is not prime. So any number that is perfect square are not prime. Third, for all integers and greater than 2, I would say for any integer greater than 2, for any integer and greater than 2, if there exists P and Q and P and Q are coprime such that N equals P times Q and P's range is greater than 2 Q, and if such P and Q exist, if P exists, then Q exists. Q exists, then P exists. If such P and Q exist, N is not prime. In other words, let's say S equals root N square Gaussian symbol. We take Gaussian symbol and root N of Gauss symbol, Gauss function. We say let S. Then we can draw the range like this. Here 2 N S since P is smaller than Q, then P is in this range. P is in this range, and Q is in this range. If we denote an equation inequality, then P's range becomes 2S. Q's range is S, N. The reason I do not put equal sign here, equal symbol here, equal symbol here, is because this condition, second condition, perfect square. If we have to put equal, then it should be perfect square, so we don't need it. I will talk more about this later. For example, if n is 21, for example, n is 21, then it means 3 times 7, n is 3 times 7, n is PQ, P is 3, Q is 7, so P is 3, Q is 7, n is 21, and S is square root of n, 4.58, and if we take Gaussian number, then it would be 4. So S would be 4. So this equation holds, and this equation also holds. So N21 is not prime. Is not prime because PQ exists. Then you may wonder how I get this n root n, this boundary. How I get this boundary. So I will summarize. It can be summarized n P times Q. It means for n modulo P equals 0, it means certain number P can divide number n, where P is greater than 2 and less than square root n, like this. If this equation holds for some number P in this range hold, then n is not prime. In other words, if n modulo P equals not zero for all P in 2 square root n modulo P is not 0 for all P in this range, then n is prime. So this and this is the same thing actually. In this case, for some P, for some P in this range. I will explain how I got this number. I will explain how I got this number. In high school mathematics, we learned something like this. 2 over a plus b equals greater than or equal to square root A times square root B for A and B greater than 0. This inequality actually means two things. If A is not B, A and B are not equal, then 2 over A plus B is greater than square root A square root B. Second, if A equals B, then 2 over A plus B equals square root A times square root B. So this inequality actually means two things. Please note that A square root A times square root B, its maximum is in this case. So if we compare this equation with this one, so we let P and we let Q, then we can put like this, P times Q, and here it becomes 2. Since P equals root A, P square is A, like this. So we can put P square, Q square. If P and Q are equal, P is Q, they are the same, then it gets maximum. P times Q gets maximum, and its maximum holds in this case. P equals Q, this case. So this case it gives maximum, so P square, and it becomes 2 P square, it becomes P square, the same. P square means root P n square. So it actually means root n square equals P square. This means this is maximum of P times Q, maximum of P times Q, when P and Q are equal. So this P and Q are equal means this case. Compare this case. So this is the maximum that P and Q can take. So it is the maximum is this range. If the P and Q are maximum case, we are not including here. We are not including in this equation. So if we summarize it, it becomes, as I told you before, N P equals 0 means for some P in P greater than 2 less than square root n, then n is for some P, n is not prime. So I got this conclusion, as I told you before. This comes from this theory. In the same manner, P is not 0 for all P in 2P root n. For all P, then n is prime. This is the theory. Now I move to my left. Please, you have to remember these two things. They are actually the same. Now I move to my laptop and I will implement this theory in C++ code. I start Visual Studio and create a new solution. I will name it prime number theory solution, I'll create an empty solution. I'll create a simple a file. I will say prime number theory, prime number theory, include iostream, include vector, int main, I right click it. I will not use pre-compiled header. Okay, here. std vector primes int n limit. I will say initially 100 int. We put primes pushback 2 is prime, primes pushback 3 int n. We start with number 5. I will say s, n is 5, while n is less than n limit. We first take square root sqrt and I will include the CMS like this. S equals sqrt and now before I do that, I will explain the theory once again. Prime number theory. First, 2 is the smallest prime number, 1 and only one even prime number. Second, for all integers n greater than 2, if there exists s such that s times s equals n, n is a perfect square and n is not a prime. Third, for all integers greater than 2, if there exists p and q such that n is p times q and p is greater than q2 and less than or equal to q, and q is less than n, then n is not a prime. here. In other words, let S equals SQRT square root n, take Gaussian number, then for some p, if n modulo p equals 0, for p s for some p, I say if m modulo p equals 0 for some p in this range, then n is not prime. In other words, if n p equals to is not 0 for all p in this range, then n is prime. This means p is greater than s, then n is prime. We are coming back here. This is perfect square root. If s times s equals n, it means perfect square. So it means not perfect square. Then we can do further test here for auto p in primes. If we are testing n p equals 0, it means not prime. N is not prime. So we break. If p greater than s, n is prime. Then primes push back and then we break. If we break out of loop, then we comes here, then n2. Because we start n with odd number, start n with odd number. Since n started with odd number, plus 2 means n is next odd number. So we are skipping all even numbers. Now here at this point, see out the number of primes less than n limit is primes size. Now we are displaying prime numbers. To display prime numbers, I am going to make a function. Here. I have to say BCTR. If BCTR empty, we simply return OS. Otherwise, last element would be BCTR C end. This is last element. Cout. We open curly brace. Then for auto ITR BCTR C begin ITR not last element, then plus ITR here STD cout ITR and STD cout. Now we are displaying last element, then close, then return OS. Okay, so here STD cout primes. Now return. Let's run Ctrl F5. Okay, prime number of primes less than 100 is 25 elements. The primes are 2, 3, 4, 5, 7, 11, 97. To test, to examine it, so prime numbers less than 100 is 25 primes. And if we try it once again with another number, for example 1000, then we try again, then 168 primes less than 1000, they are these primes. Then 1000, the number of primes are 168. And if we want to check the prime numbers like this, we can compare these with this file, with this website, for example. So the smallest is 997 here, 997, the prime number, and 997, 997, this prime number. So this works correctly. So I will make a few changes to mod test. If you want to do some mod test, I will fix like this. For std cin n limit and n limit greater than, for example 5, then we are doing loop. Here I will put some message. I have to primes clear Okay, I will do this. Let's run it. Control F5. So 10, prime numbers less than 10, 100, prime numbers less than 100, prime numbers less than 1000, prime numbers less than 10,000. You can check the result, like 1229 less than 10,000, 10,000, then this one, 100 to 1229, 1229. So this is correct. Before I close, I will put more about this here. The reason I put this is this way. And from here, the theory becomes this. Here. So this means this is not prime, and this would be belongs to here. This concludes our prime number theory. Instead of trying to remember this algorithm, you have to remember the theory here. If you remember the theory, the theory is actually pretty simple. You can implement this algorithm very easily. In next video, I will this algorithm is not very not very efficient actually. In next sessions of video, I will optimize this algorithm using multiple thread. Thank you for watching.